dear students and the participants of the course on railway engineering. In this lecture, we will be discussing about the track junctions and its design. In the previous lecture, we discussed about the turnout design. We have solved some numericals. We discussed what are the requirements if the turnout needs to be curved or if it is to be provided for the high speed tracks. Another important thing which we discussed at that time was the inspection and the maintenance of turnouts in terms of the switches, points and crossings. In today's lecture, we will be looking at various layouts which can be there when the two tracks join with each other. It can happen that the track is getting diverted or splitted into two parts or three parts, or there may be merging of the number of tracks at a particular location. So, these aspects we will be discussing today, and whatever will be left we will be taking up in the next lecture. Starting with the track junctions. Now, what is a track junction? Track junction is a combination of points and crossings which are meant for transferring vehicles from one track to another track or enable them to cross over from one track to another track. Say I have this track and there is another track which is crossing here. So, what is the possibility of the vehicle to move to the another track? So, is the vehicle or the train which is coming from this direction will be able to go in this direction or not? If it is not, then what are the things which needs to be provided extra? Or say a track is coming as a straight track and then it gets diverted in this form. So, one track goes towards the left, another goes towards the right. So, here again we have a junction being created. So, we are going to discuss about these type of aspects one by one. Now, if we talk about the classification of these track junctions, then it can be done on different bases. Say one of the bases is using the flexure. On the basis of flexure, it can be a similar or contrary flexure. Say if we take an example here where from track 1 it has got diverted into 2 and 3. So, here the flexure is going in the opposite direction to each other. So, it is a contrary flexure condition. It can also be on the basis of the split, and based on a split they have been defined as symmetrical, unsymmetrical and 3-throw switch. Again, the another category is based on the slip, where it can be a single slip or the double slip system. There are other specific types of track junctions which are available and they are provided as per the requirements at a particular location on the railway networks. They are double turnout, crossover, diamond turnout, scissor crossover, then ventilated track, triangle. We will try to discuss some of these today and maybe some others will be discussed in the next lecture. So, let us start with the first classification. The first classification, as I said, it is on the basis of flexure. So, we are talking about a similar flexure here. What it says, the turnout continues to run in the same direction as the mainline curve even after branching off from it. So, we have this main line and it is getting a branching here. So, here the track itself is having a curvature, but at the same time there is a further curvature and the branch line is coming out of it. So, if you see in this photograph, there is a track coming from this direction, it goes towards the right hand side, it is having a curve in it, and then there is another track which is coming out of it. So, this track comes out of it and goes again maybe parallel to it, not necessarily it needs to be parallel, and then there is another one also which is coming out and it is going in this form. So, this type of a similar fracture if it is there, this is one type of a junction which can be possible. Now, if we talk about the one which is being shown here in the photograph, this is the most prominent type of a system which you may found is available when you are in the station yards. Now, the degree of turnout curve is higher than the degree of the main line track. So, you can see the curvature here. The curvature here is lesser as compared to the curvature here. So, it may happen that if the degree here is d1 degrees and it is d2 degree for the branch. So, this d2 is greater than d1. The degree of turnout curve is found out as dt is equals to ds plus dm. Now, what is dt, what is ds, what is dm? Let us look at here. So, here this is dm is for the main line, dt is for the turnout and ds is the degree of outer rail of the turnout curve. So, on the basis of this we can have this relationship that dt is nothing but the degree of the outer rail on the turnout curve plus the degree of the main line. Similarly, the radius can also be looked at and the radius is given by Rm into Rs divided by Rm plus Rs, where Rs again is the radius of the outer curve in the turnout design. The another can be the contrary fracture. Now, in the case of contrary fracture, as you can see here, the main line is coming from this side and then it allows to move in the two directions now. So, one is a turnout or maybe a branch line which is coming out of that main line. Say if you see in the photograph being given at the top, a main line is being shown here and then what we found that it keeps going in this direction with the curvature, but there is another line which is coming out of it. Now, if we look at the radius, if we look at the curvature, they may or may not be same, but here in the case of main line it is going towards the right hand side, in the case of the line which has come out of it, it is going towards the left hand side and that is why we are saying that they are contrary in nature. Now, in this case also the degree of turnout curve can be found out, which is dt is equals to ds minus dm. The ds is again the same thing, is the degree of the outer rail of the turnout curve and dm is related with the main line and dt from the t word it is related with the turnout. Similarly, in the case of the radius, it is the multiplication of Rm and Rs and a ratio with the difference of Rm and Rs, where Rs again is the radius of the outer rail of the turnout curve. Now, let us look at the another categorization which is based on the split. Now, splits as I said in the starting can be symmetrical, can be unsymmetrical, or there is a possibility that they are 3 through a split condition. So, in this one where we are talking about a symmetrical split, it is symmetrical about the center of the main track. So, whatever is the main line, say if suppose we are talking here, so this is the main line. So, its center line will be this. With respect to this center line, a track is going out in this direction as well as it is going out here in this direction. So, the deviation with respect to the center line of the deviated tracks. So, this is the center line of one deviated track, this is the center line of the other deviated track, whereas the original center line is here. So, the distance between these two, if they are same, then it means it is a symmetrical split. You can see in the photograph also the main line is coming from this direction and then it is getting splitted into two parts. The split is onto two opposite directions with equal radii, it provides an opportunity to turn in left and right direction. So, whatever direction where there is a requirement to provide the connectivity, accordingly this is going to happen. Now, if we talk in terms of what are the various components which are provided in this case, then there are a pair of points, 4 curved lead rails, 2 check rails, 1 acute angle crossing. So, there is one acute angle crossing at this location, a check rail is here and a check rail is being provided here. So, there are 2 check rails. Then this is a lead being provided in this direction as well as in direction. So, we have a 4 curved lead rails and a pair of points where it is being controlled that in which particular direction the train is to be moved. It is suitable for locations where the space problems are there, constraints are there. So, this can be utilized at that location. The another one is unsymmetrical split. Now, unsymmetrical split, if we again talk in the same manner, that if you are coming from this direction and you have the center line being provided here, and if you look at the center line of the deviating tracks, so what we found is that the distance between these two, they are different. It means it is not symmetrical about the center line of the main track. So, that is what is being written here, and still it is deviating or it is getting diverged out in two opposite directions with unequal radii. If you see in the photograph again, we are going in this direction, but the way it is taking a turn, that is different. So, if we talk about the center line here, now deviations, they are going to be different. It still provides an opportunity, of course, to turn in the left and the right direction because the track is going in that form only, and it again consists of a pair of points, 4 curved leads, 2 check rails and 1 acute angle. So, it remains the same whether it is symmetrical or it is unsymmetrical split. The third category is a 3-throw switch. Now, 3-throw switch, if you see here, you are coming from this direction, that is the main line. Now, in this case, this main line is going continuously ahead. So, it is continuously going like this, whereas there is one line which is coming out of it and it is going towards the left direction, and another line which is coming out and going towards the right direction. So, we have now 3 such tracks which are coming out here out of one track, and that is the reason why it is defined as a 3-throw switch. If you see in the photograph also, in the photograph we are coming from this main track and this main track is continuously moving ahead, but at the same time it is aligned to move in this direction as well as in this direction, or we can say if some train is coming from the other direction, then it can come and merge here together and then it will be following on the same main track. So as to control these things, again you will be requiring to provide points and switches, and the crossings will also be there. So let us look at that in this case the two turnouts take off from the main track at the same point. Now when we say same point, you can see here there is a one single arrangement of the points has been provided, and based on the requirements that if it has to go on this direction, then the tongue rail is touching this straight rail which ends here only, whereas if it has to go on this direction, then it means it is going to touch here. So the gaps are going to be created in this form, that in which particular direction the train has to move, accordingly it will happen. If it has to go straight, then it means this will come out. So you will be having the movement on the straight one, and similarly here also the movement on the straight one. It can have contrary flexure or the similar flexure, it all depends what type of requirements are there. It is used in the congested goods yards, and an entry points of the locomotive yards where only the locomotives are going to be maintained. In the case of goods yards, means this is going to the location where the goods transportation takes place. It can be loaded into the train or it can be unloaded from the train. It has two switches with each switch having two tongue rails placed side by side, and a combination of heel block is used for both the tongue rails, because now you need to have a further movement. So, therefore, there is one here and another. This is how the two switches conditions will be created at the same location. The other components are two stalk rails, three crossings, 4 to 6 jack rails. It all depends what type of a fracture is being given. If it is a contrary fracture, then it is 4. If it is similar, then there can be 6 such jack rails. So, you can see here that here we are providing the heel block at this location. Similarly, for the other case also it will be required. Then you can find here how many jack rails. This is 1, 2, then 3, 4. 4 jack rails are there. Then this is a wing rail. This is another wing rail. Here also a set of wing rail is there. This is one crossing. This is another crossing. Here also we can see that this is one crossing. This is another crossing. With respect to the crossing, there will be the wing rails being provided. There will be jack rails on the other side, and then there are two such switches being operated. It allows the movement in 3 directions, which we already discussed. This may be hazardous at high speeds, as use of the double switches may cause derailment. Now, this use of double switches here may be an issue. So, it should not be used for high speeds, or even if it is being provided on a high speed track, then at this particular location, then the speed restriction needs to be enforced. So, but this is required for high speed movement. Now, let us look at the another type. This is a double turnout. A double turnout means you are going straight as a main line and 2 branch lines are coming out of it. So, you can see there is one branch line which is coming here, and there is another branch line which comes at this location. So, 2 such branch lines are coming out of here. This is an improvement over the 3-throw switch. What is the improvement here? The turnouts take off from the main line track at 2 different locations. So, there is a location 1 and a location 2. It is not happening at the same location. Now, when we are taking this 2 locations of the switches here, then there needs to be looked at the distance d between those 2 switches, because when we are operating it, so there will be a heel block which comes here. Then here also, if it is being operated, a heel block will be here and the toe may be coming at this location. So, there should be adequate space between these 2 switches, so that the operation of the switches can be done in a easier manner. So, that is what it says, the distance between the 2 switches, it shall be sufficient for operation and throw of the point. When we say here point, we are talking about this point and the switch is on this side. Now, these can also be of similar fracture, that is both turnouts are taking off on the same side of the main track, or it can be a contrary flexure, that means the turnouts are taking in 2 different directions. So, here the one which we have shown, this is what is the type of fracture you can identify. This is a similar fracture because they are coming out in the same direction. These are mostly used in the congested areas where the traffic is heavy, or if we have to economize on the space. So, in this particular case, you can see this is a contrary fracture condition being shown. Track is going straight, but one track which has come out is going to the left side, another track which has come out is going to the right hand side. There are 2 switches being provided still here. There is one crossing at this locations and there is another crossing provided at the another location, and then the number of jack rails, wing rails, all of these things have been shown in this diagram. Now, let us talk about the another category, crossover. From the word itself probably you can make it out, it is crossing over to the another track. Say if we see in this photograph, there is one track going here and there is another track which is laid in this direction. They may be parallel tracks, or there may be condition that the another track is going somewhere other direction and this goes straight. So, now we want to have a movement from one track to another track. So, what we have done, we have provided a connectivity here. So, this is a connectivity which is being provided. So, this is a crossover from one track to the another track, allows the movement of train between the two parallel tracks. The movement is either to the left side or right side from either of the parallel tracks. What it means is that if I am coming from this direction and if I want to come to the other track, it is not at all possible directly, means I cannot take a turn like this. The possibility only which lies is that the train goes straight and then it returns back and comes in this form, but then in that case this should have an engine on both the sides. Or if it has to go in the same this direction, so it will come back here and then it will goes again in the top direction, then that means that feasibility can be there, but then it will take lot of time. The easiest thing which is happening in this particular track is that if I am coming from track 1 and I have to go to track 2, I can move in this direction, or if I am coming from track 2 and I have to come for track 1, then I can move in this direction. That means one directional movement is only possible in the case of a crossover. Now, arrangement consists of two pairs of switches, two acute angle crossings, because here also a crossing is there and the other side also there will be a crossing, with reverse curve, because this is a reverse S curve getting created, with or without the straight length in between. There may be a possibility that the straight section has been provided here, or it may happen that it is a total curved section. So, the total curved section means it goes in this form and then it takes a turn in the other direction. So, the two curves have been jointed together at the same location. This is mostly used for low speed sidings or crossings for one direction only. Now, there can be three conditions. The three conditions again on the basis of that how this crossover is happening and whether it is a all totally curved situation or it is having a straight section in between. And then when this is happening and there are two crossings which are getting created, whether the angles of crossings are same or they are different. So, on the basis of that combination, we have three cases here. The first case is the crossover with intermediate portion is straight and the crossing angles are equal. So, if I am going from this track to another track and it takes a turn, so what it says is there can be a curve here and then a straight section and then there can be a curve here. So, it will go in this form, we will have a straight section and then here. So, this straight section part is there as an intermediate portion. At the same time, this angle of crossing and angle of crossing being made here, they are same. The another one is that the intermediate portion is curved. When we say the intermediate portion is curved, that means the curve goes like this and then at this point it takes a reverse curvature and goes in this form. And still there is a possibility that the crossing angles may be equal. If the crossing angles are not equal, then it will translate into the third category. So, let us look at this crossover design. There is again a Cole's method which we have discussed in the case of a turnout. We are talking about a case where there is a crossover between the parallel tracks with intermediate straight portion and the angles being same. The angle where we are talking here, that angle is basically the angle of crossing alpha. So, angle of crossing equal for both of the cases. So, what are the things being shown here? So, this is track number 1, this is track number 2, these are the two parallel tracks and they have been connected by the turnout in the center. The center to center distance between these two tracks is being defined as d. There is a straight section between the two curves. So, that straight section is here. So, that ST, when we are talking here, that is a horizontal projection of the intermediate portion on the main track. That means whatever is this straight portion is there, we are taking it on the main track. So, this is the horizontal projection and that is defined as ST. Now, TL is the overall length of the crossover, and this overall length of the crossover will be from a tangent point on one track to the tangent point on the another track. So, this is total length. If we are considering up to this point, this is TL. And the straight portion of the crossover is between the TNC of one track to the TNC of other. So, this is a TNC of track 2 and this one is the TNC of track 1. So, in between that straight portion is being provided. So, how the values are being calculated? The straight portion of the track, which is ST, that is given by d minus g into n minus g into under root of 1 plus n square, where g is the gauge of the track, n is the number of crossings which is related with the alpha. So, n is equals to cot alpha. The overall length of the crossover, which is TL. Now, this TL, what happens is you have a straight section projection here, then this is a curved section being provided. So, this is one area and then there is another curved section provided on this side. So, it is going from this point to say the TNC point. So, if we talk about the Cole's method, that is what the Cole's method is, which says there is a curvature starting from this points to the TNC, and that is what we have solved in the case of the turnout design. So, if we go by that, it means there is a curve lead here and as well as there is a curve lead on the other side. So, there will be two curve leads of the first turnout and the curve lead of the second turnout, and in between there is a straight portion projection on the main track. And this curve lead has been observed to be 2gn. Okay, so, if you remember, that was being given under g into under root of 1 plus n square plus gn, and we said that 1 plus n square is approximately equals to n square only. Therefore, if that is being taken, so under root n square is n. So, we have gn plus gn and that was 2gn. So, here when we put the values, so it is 2gn plus d minus g into n into g into 1 plus n square under root of that plus 2gn on the other side. So, it gets solved to d minus g into n plus g into 4n minus under root of 1 plus n square. Now, it can be further simplified on the basis of the same philosophy, that when we talk about this 1 plus n square, this can approximately be taken as equals to n square. So, if we do that, then in that case what happens is this under root of 1 plus n square will be n. So, it is 4n minus n is 3n. So, it is 3gn and then there is minus gn here. So, it will be left as 2gn. So, what finally we are going to get is that 4gn plus ht, because it is 2gn plus st plus 2gn and this is 4gn. We are further being changed into the another value which we already have as st. Let us look at one of the numerical here. We have the data where the two parallel broad gauge tracks are being provided. When the broad gauge tracks are there, so g is equals to 1.676 meters. The turnout is 8.5. So, n is being given as 8.5. The center to center distance between the tracks is 5. So, this d value is 5. So, this is d 5 meters. Calculate the length of the straight portion and overall length of the crossover. So, the st is being given as d minus g into n minus g into 1 plus n square. N is known to us, g is given, d is being given. So, if you put the values, d is 5, g is 1.676, n is 8.5. we get a value of 13.91 meters. And similarly, the total length of the lead here, it is ST plus 4GN. So, ST we have already calculated. 4GN is 4 into G into N. So, what we get is 70.89 meters. So, that is the way we can solve this type of a crossover design. Let us look at another numerical here. There are two parallel broad gauge tracks. So, as soon as it is broad gauge, G is 1.676. Now, turnout is here is N is equals to 12. Center to center distance is still being given as 5. The heel divergence is being added here. This is 133 mm. Calculate the length of the straight portion, overall length of the crossover, radius of curved lead and lead distance. Use Cole's method. That means now here we are going back and we are also going to talk about the turnout design. So, we have G, D, N and D values available with us. ST value, as we have calculated previously, we calculate using the same formula, and by putting the values here, what we get is 19.69 meters. Similarly, total length of the lead, it is ST plus 4GN, and therefore, the values when they have been placed here, what we get is 100.13 meters. So, ST and STL has been calculated here. What we have to calculate is the radius of the curve lead and the lead distance also. So, radius of the turnout curve is given by 1.5 G plus 2 GN square. G and N are known to us. So, this is G, this is G and N. So, what we get is 485 meters. And the lead of the crossing, that is CL minus SL. So, the formula is 2GN minus under root of 2R D minus D square. Again, the D value is given to us here. So, this is 133 mm. So, we are considering that value. G and N already there, R we have calculated. So, if we put all of these values here, so R 485, D 0.133, what we get is 28.8 meters. Now, there is another method other than the Cole's method, which is an IRS design method, that is an Indian Railway Standard Design method. Here we are talking for the same conditions, that crossover is between the parallel tracks, intermediate portion is straight and the angle of crossings they are equal. So, in this case ST projection, that is given by D minus G sec alpha into cot of alpha, or it is D cot alpha minus G cot alpha by 2. That is the formula which is used if we are using IRS design method. And L is the length along the crossover from TNC of one track to TNC of the another track. So, that is given as again D minus G sec alpha into cosec of alpha plus G tan alpha. So, this is the crossover design on the basis of IRS method. Let us look at a numerical here. There are two parallel broad gauge tracks. Turnout is 1 in 12, center to center distance between the tracks again 5 meter. You have to calculate the length of a straight portion, the horizontal projection of the straight main line track using IRS method. So, G, D and N, they are given to us. Angle of crossing we need, because here alpha value. So, angle of crossing is to be calculated. So, N is equals to cot alpha, that is the formula which we are considering, and we get a value of alpha here. So, once we have got the value of alpha, then we can put these values into the equations which we have, say ST D cot alpha minus G cot alpha by 2. So, this is 5, this angle we have calculated, G is 1.676. So, what we get is 100.29 meters. Similarly, the lead is D minus G sec alpha into cosec alpha plus G tan alpha. So, we are again placing the values here. Here again G and alpha, so we get 19.91 meters. So, this is how the crossover can be designed depending on what type of information is available to you and what are the values which have been asked. Now, here the other two cases formula have been given. The first one is the crossover between the parallel tracks with intermediate curved portion, and still the crossing angles they are equal. So, you can see here on the right hand side that diagram is being shown. So, this is angle alpha as well as this is angle alpha, and we have the curved section. It means this is the point of contact between the two curves, which is coming in this direction or in this direction. So, two curves are being provided here. So, the radius is going to be equal in this case. So, if we solve this particular geometry, then what we get is that this S, which is the projection on the main track, main lead line, with respect to the distance or the movement between the one TNC and the another TNC, that means on one track as well as on the other track, that is given by L minus 4 GN, where L is the overall this length, which is a combination of the curved leads here and the straight section. So, that is defined as under root of d into 4r minus 2g minus d. So, this is a case when both crossing angles they are same, but if they are not same, the formula will remain the same. The only change is because this is an effect of 4gn, means this is an effect of one turnout here and another turnout on that side. So, now it will get splitted out because you have two different values, because the crossing angles are not equal. You have alpha 1 and alpha 2, that means you have the number of crossing as n1 and n2. So, that is the reason this value will get separated out and it will become L minus 2g n1 minus 2g n2. And similarly, in the case of lead rail, it will become under root of d into, previously we talked about 4r, now it is 2r1 plus 2r2 minus 2g minus d. So, more or less the things remains the same, only thing is now we are getting splitted out because we have two different curves being provided. So, a numerical on this, let us look at it. So, there is a one turnout of 1 in 12, center to center spacing 5, intermediate portion is curved. We have to calculate the two components. So, here G is being given, D is given and N is given. The radius of turnout can be found out as 1.5 G plus 2 G N square. So, if we put the values here, G is 1.676 and N is 12, what we get is 485. Now, the lead is under root of D into 4 R minus 2 G minus D. So, R we just calculated, D was given, G is known for broad gauge track. So, if we put these values here, we get 98.27 meters. The projection is being defined as, from this particular length we reduce 2 GN on one side and 2 GN on the other side. So, it is minus 4 GN. So, if we put minus 4 GN, what we get is 17.82 meters. Let us have another numerical here, where there are again two parallel broad gauge tracks, but the turnouts are 1 in 12 and 1 in 16. Now, there is a change. So, alpha angle is changing, N is changing. So, we have N1 equals to 12 and N2 is equals to 16. The distance between the two tracks is still being given as 5 meters. So, D is 5 and because it is broad gauge, so it is 1.676 meters. So, now we have to calculate the radius of the turnout. The formula remains the same, but the N value is different. Therefore, we will be having R1 and R2. So, we calculate R1 and R2. So, R1 is being calculated here for a turnout of 12. It is 485, but if the turnout is 16, it comes out to be 861. So, that is R1 and R2. So, calculating the value of L, we have 2R1, 2R2 minus 2G minus D. We put the values here. What we get is 115.84 meters. Now, if we calculate the horizontal projection here, that is L minus 2GN1 minus 2GN2, where N1 is 12 and N2 is 16. So, if we use these values here, what we get is 21.98 meters. So, we have looked at all the three cases, that how all the three cases can be solved so as to compute the components which are required so as to design and lay this part crossover. So, with this we close our discussion now. We discussed about the certain layouts of the track junctions. They were classified on the basis of flexure, they were classified on the basis of a split. Then we discussed about the 3-throw switch also, double junction, and then finally the crossover was discussed, and the various methods of calculating the component leads, curves, the radius, etc. of the crossover, they were discussed. Thank you. We will be meeting in the next lecture.